Good afternoon. My name is Robert Kroeger, and I'm going to talk to you about caching patterns for building offline web applications. Where did my slide go? There we go. This is the sort of design pattern we use underneath the mobile Gmail application that you might have seen on the iPhone or the Android. So, of course, first question is, why build a mobile web application at all? Instead of, say, a native application that runs directly on the phone. Web applications, they tend to have two large advantages that Vic alluded to this morning in the keynote. First off, phones are pretty small. I mean, our phone is, it's better than the Unix workstation I had on my desk 10 years ago, but it's still really tiny compared to our data center. You just can't run the kinds of apps on the phone that you might like to. Another problem with the phone, with building native apps, is that it's hard to distribute to phones. So much easier to distribute a web app. There's no App Store approval process. You know what I'm talking about. You'll get to launch on the schedule you pick. You don't have to wait for someone else to decide that it's okay to have your code on their device. There's no mobile provider in the way, and you can update frequently and fix bugs, maybe even weekly, maybe even daily like we have had to do lately. The problem is that sometimes building a mobile web app is kind of slow. The server has a nice, fat connection to the internet, but the phone has a little skinny, not-so-fat connection to the internet over Edge or 3G. And there's two problems to this connection. The first is it can be very high latency. It can take seconds to establish a radio connection. And the other big problem with this is it comes and goes. I don't know if you've ever tried web browsing on Muni or any other public transit system, but sometimes it's going along great, and then all of a sudden it's like, oh, no signal. And this is kind of disappointing, especially if your application is synchronously connected to a server over the pipe. So how can we fix this? We fix this, at least in mobile Gmail, with caching. We wanted to split the UI from being dependent synchronously on a connection to the server. And we did this by inserting the big green cache, and that's a pun and it's kind of bad, I'm sorry, between the actual UI and the rest of the system. So you see that at the bottom of the lower diagram where we've placed this cache that's connected to the UI. And so as a result, UI updates needed to repaint the user interface. They come out of the cache, they go to the UI. And obviously, the user makes modifications to the state of the application. That gets written into the cache. And we have this nice little loop that's entirely local from the user interface to the cache and back. And then, of course, the cache, asynchronously to the user's interaction with the system, pushes these changes to the server. And, of course, responses come back from the server and get written to the cache, and the cache has to merge all this together. And so we've divided our application up into a part that's local and synchronous, and a part that is asynchronous and involves the connection to the network. So let's look inside the green box, the cache pattern itself. So it has 4 basic data flows on the left side. The red ones are the data flows to the user interface that are intended to be reasonably fast and immediate. And on the right, we have the sort of asynchronous, arbitrary latency interactions with the server. But we need a place to keep all the data that we're storing in this cache. And so where do we keep it? We want some kind of persistent storage in the browser itself. And that brings us to structured storage. So HTML5 and Gears, they both add some kind of structured storage to the browser. And structured storage is really great for implementing this cache. It's a largely complete SQL database. And it's all on the mobile device. We don't have to go off over the network to fetch it. And we can actually get to it even if we don't have a network connection at all. It has 2 really great properties. first off is it's persistent. If the browser crashes or is terminated by the operating system because you ran out of memory, it's still all there. All your edits stay there in the persistent structured storage. And of course, it also implements the sort of standard database ACID properties, atomic and consistent and durable and all that goodness that they taught us long ago in computer science class. And that's also really helpful in the case of, hey, look, the operating system just tossed the browser. And that way you don't lose your edits. Now, there's a problem, and the problem is that HTML5 and Gears have really quite radically different programming models for how to get access to the structured store. Gears has a synchronous interface to the database. So what does that mean? It means that you have the nice little JavaScript thread running your code, and when you want to make a call, with a Gears call to fetch data out of the database, you make a function call into Gears. That's the sort of red database action code there in the top diagram. And then the Gears code processes. And then it returns in the standard kind of, Unix system call kind of way to the calling JavaScript thread. HTML5 is different. And, it starts out the same. The JavaScript code makes a call to an underlying or a SQL thread that runs database actions. But that sort of runs separately and independently. And it doesn't return data to the JavaScript. Instead, it calls back into the JavaScript at some arbitrary point later. Now, this is sometimes harder to program, but it also has the advantage that other JavaScript, like button clicks, can happen in the meantime. So we can kind of sum up this difference in this nice little table here. On the Android device, we get SQL databases, we get via Gears, so it's a synchronous programming model. And on the iPhone, we get HTML5 databases that are asynchronous. And so we have, that little red problem area. We can't have structured storage on both platforms the same way. They have different programming models. It's a pain. So we have a solution for this. It's something we call the Web Storage Portability Layer, which is a long descriptive name. I know it's too long, and I'm going to frequently say WSPL instead. WSPL is you write your cache or any other kind of structured storage web application to a single common programming model. And on HTML5 devices, the nice little wrapper translates that into HTML5 calls. And on Gears, we emulate the asynchronous programming model with a Gears worker that runs asynchronously to the mainline thread and does all the database, all the synchronous database actions using Gears. And this is, as of yesterday, at least, this is now open sourced from code.google.com /p/web storage portability layer. And I encourage you to go have a look. And eventually, the material in these slides, at least some of it, will get added to that site. So thanks to this WSPL layer, we've solved the whole where to keep the data that we want to put in our cache. We keep it in some kind of arbitrary WSPL wrapped database that sits underneath our web application. And you'll see there's two arrows going into and out of the WSPL layer in the picture. And this is because WSPL has to provide an asynchronous programming model to be compatible with HTML5. And so one arrow going into the WSPL layer, those are calls from the cache, and then there's callbacks, that's the other arrow. So the underlying kind of mechanism taken care of, we can talk about the sort of the cache structure. And this is very much the architectural pattern that is found in mobile Gmail, albeit with some tweaks and differences. We can talk about the cache pattern in detail. So it's kind of busy, so sorry, but it's not that, it's pretty complicated in some ways. The first thing that you'll see is I've doubled up all the arrows because the interface to the WSPL has this, one call in one way and then call the other way, and so all the other interfaces on this cache structure have to be bidirectional as well. So I've also given each of these calls names, and that's because there's a demo app that comes with the WSPL distribution that I called Simple Notes that actually uses these names in the code. So if you take, for example, getValues, that is a call from the UI into the cache to get content, and then there's a callback, value callback, logically enough, that delivers the content from the cache back to the user interface. And so what about this simple notes thing? So the simple point of simple notes is essentially just to make all of this more concrete and to demonstrate the use of WSPL and to provide sort of a concrete, somewhat simplified, getting started implementation of the cache that people are free to use. You can extend it any way you want. First off, Simple Notes is really a toy application, and because I had too many years of college math, the server side is an exercise for the audience. And the first person who writes it gets some swag. And you should go to the App Engine talk and learn how. Now, with that little Tom Sawyer moment out of the way, Simple Notes has 3 basic pages. They're essentially just different divs, and they are hidden and displayed by the appropriate CSS modification. There's a list notes page. There's a show an entire note page, and then, of course, a edit or create a new note page. And Simple Notes itself is really not very useful, but the cache component is pretty much complete and is a good starting point for building an arbitrary cached application. So there's some important design aspects to how you actually implement a cache of the kind that we're talking about here, and they all sort of come out of the hardware literature because people have been building caches and hardware for years. The first thing is we need to be able to determine if a requested entity is in the cache or not. So we need some kind of hit determination mechanism. In Simple Notes, we keep a contiguous range of notes in the cache at all times. So it's pretty easy to decide if we have a node in the cache. If it's between two, if its index is between a pair of numbers, yay, and otherwise we have to go fetch it. We also have to have some refresh mechanism. We have to have some way to know when to fetch content, new notes from the server, and how to add them to the cache, and what to do about, of course, getting rid of the notes we don't need, the eviction process. And finally, we need a coherency mechanism. We have to figure out in the client how to join server changes and user changes together in the cache such that you don't lose the user changes, and they don't like that. So now some more details. So first off, Simple Notes is implemented as 2 separate database tables. You'll see it's pretty standard SQL code there. Also, you'll notice that we use the WSPL statement object to wrap our SQL strings. This is just a convenience thing to simplify parameter substitution so that it works both on Gears and HTML5. And also we have some statements down at the bottom to select statements to go to the database and find out what are the endpoints of the range of notes that are in the cache. And so this is what would get, these 2 statements would get, the creation statements are what to build the database, and of course finding the endpoints of the cache happens at the setup of the application. We chose to separate the cache's backing store into these 2 separate tables, into a write buffer table and a cache notes table, in order to divide state from actions. The state is the sort of the model that the user is seeing and interacting with, and the actions are things that we need to preserve because we're sending them to the server or merging them with refreshes that have come from the server. And by putting these in 2 different tables, it provides a nice simplification of the architecture. And this sort of arrangement of a table of actions and a state table corresponds to the hardware notion of a write-through cache. This is kind of one of the simpler read, modify, write hardware caches that one could build. So here's some code. And its goal is essentially just to set up This is all in the distribution, so if you download it, you can have a look at this. It creates the tables, and it loads some triggers, and we'll talk about the triggers shortly. And it determines, as I said, what's already in the database, the last two selects. So one of the things that you should note about this piece of code is the use of execute all. Right? This is a convenience function we added in WSPL, so you can pass an array of statements to the library and say, just go do all these. As opposed to in HTML5, just out of the box, for every single separate SQL statement, you have to have a call to HTML5 to fire the correct piece of SQL, and then a callback handler. And this was just made life simpler. Also notice that asynchrony comes up even here. We don't know if we've actually completed the creation of the tables and the addition of the triggers, etc., until some callback is fired from inside of the WSPL library. And so we can't tell the UI that we're done without a callback that we provide in the callback argument. So let's talk about the sort of data flows through the cache in a little more detail. This is the case of the getValues, so your sort of basic, give me something out of the cache query and get a response. And so the basic idea is the UI will call into the cache to obtain, say, a note or a list of notes. And there's a whole sequence of WSPL calls or HTML5 calls, as case may be, that are required to implement that. You see that at the bottom. We have to first create a transaction, and then inside of the transaction callback, we have to dispatch some SQL statements and then get the results. And then finally, once we've accumulated all the results with accumulated results, of course, we forward the response, the complete entire result set, back to the UI for display. The implementation looks a bit like this. This is just essentially a wrapper that fires off the right kind of sort of larger helper method. And there's two things wrapped here. First is get notes, list of notes, and the other one is get just one note. And get one note is much simpler. It only has to obtain one thing, and so we just kind of skipped over it. So the code looks like this pretty much. So it starts about there, really, sort of in the middle. I mean, all the stuff above is the definition of callback functions. And then the first thing that the mainline code does is it creates the transaction, like I said. And then that transaction is the in-transaction getNotes function that you see second from the top in the list of callback functions. And then inside that transaction, we run the list cache notes SQL statement, which of course just does a select over all the notes in the database and returns that. And then that gets accumulated in the accumulate results callback. So inside the transaction, the SQL statement is sent to the WSPL library, and then the callbacks aggregate in the array notes, and then the transaction ends. So this little colored diagram at the bottom shows sort of the time sequence. We have the start of the function in red, and then the transaction boundary is defined by the sort of yellow region, and we can control the transaction boundary by explicitly creating the transaction and providing a function to run inside of that transaction. And then that first function that's run inside of our transaction, it dispatches the SQL that we want to have execute. And then the callback also runs inside of the transaction and could, in theory, dispatch yet more SQL, etc. And then finally, when all the functions that were invoked with a valid transaction object have finished, then the transaction is closed and the changes, if any, are committed to the database. So there was a little piece of code in there where we determined if something's in the cache or not. As I said earlier, it's really very simple in simple notes. We just have a list of notes, and we store their endpoint ids, and if you're in the range, yay, and if you're not in the range, we must go fetch the note from the server, or range of notes from the server. the next piece of the cache is handling user changes. So this is the case where the user makes some modification, and we want to put that into the write buffer and then apply that result to the actual state of the cache. And we actually do the application of the change from the write buffer to the cache state with a trigger, and then finally acknowledge the change to the UI. And triggers are very, very useful function in SQLite and HTML5 and Gears. They really help improve performance and simplify development. And as a result of the use of triggers, the actual JavaScript code for making a change to the cache, to user that UI change, is very simple. All it does is a little piece of SQL that inserts an action into the write buffer. Now, why use triggers? For a complicated update, like updating the cache state from an entry in the write buffer. Triggers help avoid ping-ponging, which can be very expensive. Rather than having the case where you see at the top, where we run a little bit of JavaScript, we start a transaction, fire off some SQL, the database does some stuff, the database calls back, the JavaScript does some stuff, executes some more JavaScript. Rather than have that sequence of back and forth, instead we have one little piece of JavaScript that starts the process by writing to the write buffer, and then the trigger does all the work. The transaction's shorter, and there's no need to go back and forth between the threads, and it just runs vastly faster. Especially runs faster if you're emulating this model of the two threads with Gears workers, and this also, by making your transaction shorter, you can work around a number of somewhat nasty bugs in the HTML implementations currently shipping. So here's the actual trigger code for simple notes. The triggers for mobile Gmail are much more complicated because you can do more to your mail than just add a note consisting of note text and a subject. But the basic idea is the same. We have something in the action queue and copy it into the cache state per se. There's two statements here. The first just does the copy, and the second updates some state bits in the action queue to track that we've actually done the copy so we don't do it over and over again. It's worth noting that the trigger is the only way to do a whole bunch of SQL statements without this ping-pong process. It's the nicest way if you have a whole bunch of SQL and you just want it to run without worrying about its result. It's the nicest way to do that. Makes it it's the easiest way to write. The next sort of main flow in the cache itself is insertUpdate. And insertUpdate is perhaps the most complicated flow through the cache. It's the case where we've received the application, the mobile app, has received content from the server, and we have to combine that content with the existing contents of the cache and any changes the user has made to the cache that haven't yet reached the server. So the basic idea is that it all starts as a result of the callback on an XHR. That's the insertUpdate in the top right. And then we do some work to put all the changes into the cache. Once again, we use a trigger to replay actions that have not yet reached the server against the changes made by the server on the cache. And finally, if this was all in response to a cache miss, we have to send the new updated results back to the UI, because the UI will have been waiting the entire time for this round trip to the server if the desired value was not actually cached. Now, it could have been doing useful things in the meantime, but it wouldn't have been able to show whatever that requested entity was. So, here's some sample of the code. The basic idea is that we start by creating all the statements necessary at the top, that's the for loop, to write the server's updates to the cache. And this code presumes that The changes are sent as a JSON encoded array. There's just an array of little JavaScript objects. The next thing we do is we remove, that's the eviction statement, we remove all of the notes in the cache that are not part of the desired request. And we have a very simple eviction policy and simple notes. We maintain a range of I through j of notes, and everything outside of that, we just throw it away and assume the server has kept it. The next thing we have to do is we have to mark the contents of the write buffer, the actions to reapply, so they can get reapplied to what we've just put into the cache, because these series of updates have possibly destroyed user changes that haven't reached the server. We need to update at this point where the little arrow points the notion of what is in the cache. And it's important to do this at the start of the transaction as opposed to anywhere else, so that any subsequent transactions will see correct state. And JavaScript code that is not yet inside of a transaction will also see what state it will find in the database when it's allowed to have its transaction run. This kind of, I don't know, I used to like drawing diagrams and try to plot out these things. It can be a bit tricky with the whole asynchronous callback model, figuring out where you actually are with regards to updates in JavaScript and updates in SQL, because there's no sort of, they can happen overlapped. Finally, if this particular update is a result of a cache miss, we call back to the UI, delivering the content that we received from the server. Finally, we have this last case, which is where getValues is handling a cache miss. And in this case, we will have had a getValues call enter the cache, and it needs to do, it needs to obtain from the cache all of the requests it should send to the server prior to sending the query. And then only after it's done that, it sends this aggregate bundle of updates plus query all to the server as one, so that the server can apply, prior to generating the query result, all of the as yet unseen user actions. And this should be starting to look pretty familiar by now, this code. It's the same basic structure. We begin at the top by accumulating a bunch of records that we need to send to the server, and we mark the state of the records that we are sending to the server in the write buffer as being in flight, and then we send those plus the query upstream to the server via XHR. So this diagram should hopefully make this a little bit more clear about how we're maintaining consistency. The gray cloud is obviously the network, and the green box is the contents of the write buffer over time. And way out there at the left, the user has made, prior to the start of this diagram, one change that is stored in the cache as change 1. And they then do something that requires, that causes a cache miss, and so the UI, the cache is going to fire off a fetchFromServer call. And what does it do? Well, it obtains update 1, and it suffixes that with the query, the desired object that's wanted, sends that to the server. Well, let's say it fails. And the XHR times out, you're offline, you needed to authenticate, you lost your cookies, something bad happened. Well, in that case, the ActChange response from the XHR comes back, and we mark in the failure callback that, hey, we tried, we sent the action, too bad, and we tell the UI we couldn't satisfy the request. More time passes, the user keeps using the application, they make another change. This would be change 2 via the applyUI change there. So now there's change 1 that has not reached the server, and change 2 that, well, we haven't sent to the server yet, but we don't know if it would fail. But maybe by this point, the user's gone online. And so we once again call fetchFromServer, to fetch more content. And once again, we need to extract from the write buffer changes 1 and 2, and then append to that the desired query, Q, and that all goes to server as one big bundle. And in this time, it succeeds. And so the server responds positively with the desired query result and acknowledges it's received changes 1 and 2. But in the meantime, because it takes time for things to reach the server and for the server to do things, the user's made another change, change 3. So if we replace the cache contents with the result of the query that we have just sent to the server, we will lose change 3. And that's the point of the reapplication, is that first we update the response. That's the Q response there you see in the diagram via insertUpdate. And then we reapply the change 3 via the trigger that I already discussed to make sure that now the state of the cache is whatever was on the server at time Q plus change 3. So some miscellaneous tidbits that are worth talking about. First, I've assumed that all the content going up and back to the server is always some kind of JSON encoded content, probably sent via XHR post. If you're using app cache in your application as well, it almost has to be post, and it probably can't be get or put. So I guess put is post. And then, for all the missing bits I haven't talked about, most of them are in the distribution and should run. The whole asynchronous programming model that you see in HTML5 databases and you see in WSPL for the same reason can be kind of difficult sometimes because it sort of changes the order of your code. It makes the order it runs in not necessarily even remotely like the order it's written in. So it's a good idea to have planned out what you think the order of the code is, its execution order, and to invest in some good logging frameworks for your code before developing with HTML5, so you know what is happening when. It can be very hard to deal with. Another important tidbit with HTML5 is triggers they really make life so much easier. The SQL in the trigger, it runs in the order it's written in, so it's easy to figure out what it's doing in comparison to the JavaScript callbacks. And it also makes it a lot faster to develop. You can make some very rich, pervasive, and well-structured changes to your database pretty easily in SQL. Of course, you can also damage it. So, my advice is use triggers as much as you can. They make life easier. The other thing is that they run on a separate thread from the UI thread. And so the fact that a trigger is progressing does not block the execution of the UI thread where the user is clicking and you're rendering the results of changes the user's made onto the screen. And that helps keep the application responsive. And finally, I've sort of glossed over some sort of tricky problems in the sort of simple notes example code. In particular, at least on a mobile device, the database isn't actually fast enough to serve as the model in a model view controller architecture for your application. You need some kind of memory-based model that is served from the cache. It's also the case that the database size limits, at least on current generation iPhones, is such that you probably will find that your model in memory and your model in database will be about the same size, which has some opportunities and some additional issues having to do with making sure that you evict the right stuff. I mean, in theory, you could keep different things in cache and in RAM model and sort of double up how much you have available to show to the user. Finally, Simple Notes does too much data traffic. When you refresh your cache in Simple Notes, we just grab all the notes over again that are within the desired range. This is clearly not the right way to do things. The right way to do things would be to grab only those notes that have actually been modified on the server. And one way to do that might be to add some kind of date stamp to the tables and then send that to the server. And And then the server would say, yes, these ones have changed, and only send those back. Now, that would require, as part of servicing cache miss, a trip to the database before you can send the query to the server. And that means that it takes longer to service the cache miss, and that increases latency if the cache is empty. So these are kind of lots of interesting design trade-offs to be worked out. So, in summary, the cache pattern is workable in real products. It's actually what we're using in Gmail for mobile. The WSPL library is also workable. It's actually, if you've used your iPhone with Gmail, this code is live and shipping, WSPL, so it does actually work. And it does provide a workable local storage solution across both iPhone and Android platform devices. So that's sort of the end of the presentation. I invite questions. You can go to the microphones, please, if you have questions, or we can use the moderator. You can find it. Oops, wrong window. Questions?
Hi. How well the database is secured? The security of the database?
The security of the database? So the security of the database is, in our case, left in the hands of the browser. The browser enforces domain-level access in the sense that if your app is served from www.google.com, only other apps served from that domain are allowed to access the database. Obviously, if you have shell access to the device in question, the security doesn't exist. Like if you've actually logged into the device, if you're using an HTML5 database on your desktop, you can go find the actual file in the file system and edit it, as you might expect.
Okay.
Does that answer your question?
So it's stored in the clear text, or?
Yeah, they are.
Okay.
I mean, the presumption being that a web application cannot get access to the database without being served from the same domain as the web application that created it. And the browser is the gatekeeper.
Okay. Thank you.
Are the domain-based security mechanism, is it related to single origin policy?
Yeah, that would be the right way to say it. Thank you. More questions? Are they appearing here? I'll repeat the question for the benefit of the recording. Is there a limit on the amount of data that can be cached, and are we caching to the SD card? So where the data goes is under the control of the browser. We personally don't control that. The HTML5 spec says nothing of where the browser or platform should put the data. It might put it on the SD card. It might put it in some other kind of store inside of the device. On your desktop, it puts it on your hard disk. The data volume, the current iPhone 221 hard limits your database to 5 megabytes per domain. Gears has a much more flexible policy in that we could ask the Gears database to be much larger, and as long as the user has agreed in the Gears permission dialog, it could be much larger. The size of the database is something that's evolving. The HTML5 specification is sort of fuzzy about what exactly should happen with database size. Like, what should the limit be? They say that there should be some sort of reasonable default, and that perhaps the user agent could ask the user if they wish it to grow. And this is how it works in recent WebKit nightlies, and is what is supposedly supported in iPhone 3.0.
So how do you foresee the performance problems of on-device or in-browser databases? Would it make sense to invest in making like a JavaScript ORM, or just to wait for the databases to get faster?
So the database is, I think, the database is largely slow, I believe, because we're spoiled by the desktop, and it's highly not slow on the desktop. A flash store on the phone is not a high-speed random access storage device by the standards of modern SATA disk, and that's why I think the database is kind of slow. But I don't really know for sure.
But is this database usually SQLite?
Yeah, it is. It's SQLite.
So this could be addressed in SQLite.
Yeah, that would be nice. I think if they sped up SQLite. It's fast enough for caching applications if you're not relying it to be the application model.
Okay, thanks.
What's your experience been with indexing and kind of other, more tuning, kind of tunables and stuff like that you'd expect from a SQL implementation?
So indexing is a win in SQLite. It's not as much of a win as we'd hoped for. We got maybe 2x improvement with indexes. The performance tools are difficult to use on the device itself. You have to have jailbroken your phone and run the SQLite command line that is, of course, from the jailbroken website on the device to actually access the database on the phone itself, because the performance results on the desktop mean nothing. Everything happens instantly, essentially. So
what's the that's the iPhone story. What's the similar story for the Google device or other?
The Android?
Yeah.
So once again, you have to run SQLite on the device. It's included in the Android SDK. It's the same basic idea. You log into your Android device and you can profile your database as you see fit. The Gears implementation, the actual database interface in Gears, perhaps because it's synchronous, is faster than the iPhone implementation. But implementing the asynchrony through a worker has some is slower than the HTML5 implementation of the same thing, because it's in HTML5 you have a native thread running the database, and in WSPL we have a JavaScript thread running the synchronous database.
Thanks.
Hello. Thank you. It was very informative. The question I have is, the last time I checked, a custom Android app did not directly support Gears.
So this is a web app, right? It runs inside of the Android web browser, and so the Android web browser has Gears available. It's simply a matter of calling the requisite recommended code that is available from the Gears website, and it will put up a permissions dialog, and the user will need to say yes, that it's okay for Gears to be available to this particular web application. And once that's done, you can use Gears calls in your web app on Android.
Okay. And just to, whether I got it right, I know that browsers on Android were supporting Gears, like the browser app. But if I say I create my own app XYZ, I mean, my understanding the last time was it does not invoke Gears, or I cannot.
I don't know.
Okay. Thanks.
The answer to that.
Hi. Is the API going to evolve into something like EJB3, like object-oriented stuff? Entity beans.
Which API?
The WSPL.
So the WSPL API should look very much like the HTML5 database API. If you're thinking that we could add some kind of JavaScript object relational mapper, you're right, and it might happen. But no promises.
Okay.
More questions?
So what's the Google Gears roadmap looks like? Because we have HTML5 now, and you guys are going towards HTML5, so.
Yeah. I guess the simple answer, which isn't really useful, is that they're converging, that eventually there will be one API that is blessed by the WG working group that everybody uses, and people are working very hard on making that happen.
So would you recommend us using Google Gears at this point, or?
Well, so one of the nice things about this WSPL library is that it protects you from this choice. You can write database apps now against an HTML5 API, and they'll work on Gears too. So that's what we decided to do. We had to support Android and iPhone, and so we built this library that let us do it. If you have a need to support both platforms now, then I would recommend you try out our library, because it will do the job. And then as HTML5 becomes available natively everywhere, our library will get skinnier, and you won't have to change your code.
One related question is, do we have WSPL available on the desktop, I guess, on any browser? Or
it runs in Android and Chrome and Safari correctly.
It should be okay. Thank you.
More questions? Oh, screen saved. Wants my password. Yes, it would be really nice to have an ORM system. We actually started writing one and never really finished it. The reason why I was writing it, and the reason why I abandoned it was that it wasn't advancing other features that were being asked for by managers. And it was not at the time, we didn't see a good way to make it both sufficiently general and fast. It would be, hypothetically, it would be nice to have some kind of compile time tool that would read say a JSON object definition and would construct the appropriate SQL. So that's where our thoughts are with doing ORM for JavaScript. Well, I think we can all have coffee early because if there's no more questions. Going once, going twice.